So, all right, look, do this for me. Someplace off to the side. Maybe write these things down. And then you need more information. So let's start with this. Identify the forces acting on your object. That's the first thing you need to do. We already know that this is a second law problem. We saw it, it accelerates. So I can skip the is it a first or a second law problem. But you have to be more sophisticated. Is it a first or second law force problem? And is it a first or second law torque problem? So was it clear that it accelerated downwards when I released it? So we know it's a second law force problem. Is it clear that it spun on its way down? Then it's also a second law torque problem. You should evaluate every object to see if it's a first or second law force problem or a first or second law torque problem. After you've done that, you need to identify the forces acting on the object. I shouldn't have to say what forces exist anymore, right? You have a long list of them. And not even that long, right? I think it's 5. Tension, weight, normal, friction, drag. Those are the forces we have. Well, which forces do you think we have to worry about here? All right, tension and weight. So I'll write weight's happening here and tension's happening here. And I think the tension is less than the weight because it accelerated downwards. I'm going to choose downwards to be the positive direction, right? That's your next step. Identify a direction that you will call positive. So I've identified the forces. I've drawn a diagram indicating where they act and how they occur. I've indicated a direction I call positive. And now I write in my force equation. mg minus tension equals ma. That's it. I'm done for forces. It generated a relationship. Right? Add up all the forces, set them equal to ma, taking direction into account. These were your steps. Do I need to repeat all them? Because you should have them. Because the next part of this is just to shift over and do all the same thing, but this time for torque. So I have to pick a pivot point. What's a likely pivot point? Okay, so we'll pick the center as our pivot point. That's the only difference for torque, is that you have to identify a pivot point. This makes reasonable sense. I have identified a pivot point. Now, I said the net torque equals I alpha. So I have to address both sides of this equation. It's a little more complicated for torque, but not that much. So looking at my forces, do these forces cause a torque? Is there a force that is acting with a torque arm distance that's other than 0? Which one? Tension. So I'll remind myself that every torque has 3 parts. Those are the 3 parts. When I look at this picture, it appears that the tension is acting a distance r away from the pivot point. So I will identify that r is the torque arm, T is the force, and I can see that, like a pulley, it's acting at an angle of 90 degrees. You guys just wrote out torques that didn't have any meaning. I saw them. Some of you had 2 or 3 of them out there. I don't know why some of you had 3. The best would be 2. But I think there's only 1. I don't think the weight causes a torque because the torque arm distance is 0. Again, identify each force, and then from there, based on your pivot point, which of those forces cause torques. Write out the torque. Your next job is to identify the moment of inertia. Again, we don't have to do that for net force. We do have to do that for torque. So I gave that to you. I said it's a disk. So 1/2 mr squared, the moment of inertia, times alpha. All right, we have an equation that could be used to help identify the acceleration of the system. And I can reduce this equation too, right? I can divide one of the r's out, and I can take the sine of 90, which is just going to be 1. And this will be T equals 1/2 mr alpha. Now, here's the problem. I want the acceleration of the system, and that's this number, right? That's A. T is an unknown. I can't have T in my answer. Over here, I thought maybe I could bring these two things together, right? Do substitution, but won't that just be substituting another unknown into my answer? Which is why you have an additional step. So we identified the torques, we set them equal to I alpha, that generated a relationship, but you have to go one step further. You have to ask yourself, is the linear acceleration connected to the angular acceleration? This is another step. It should be in your list of things. Because if it is, then you can put it all in terms of A. If this isn't, then you can't. So, does the rotation of the disk align with the acceleration of the disk? Yeah. If it unrolled one rotation, it would have gone downwards one circumference. That's what makes those things equal. Yep.
You're never going to give us a problem where they don't want.
Sure, why not?
Oh, okay.
But let's focus on getting you the ones where they do align, right? That's already a toughie for you. Okay? And I'll show you an example where they don't align right after this. Okay? Just show you an example. Don't be worried. But let's focus on this. Go ahead. You have a question?
Yeah, will we be given the 1/2 mr squared?
Yeah, you won't have to memorize moments of inertia. What I did say in class was that you should be able to rank things based on what their moment of inertia is. Like you should know that a ring has more inertia than a disk. Right, I said that in class. And so all the round objects, you should be able to rank them based on their moments of inertia. So ring, disk, hollow sphere, solid sphere. If I said put them in order from hardest to turn to easiest to turn, you should be able to do that. But I don't expect that you know that it's mr squared, 1/2 mr squared, 2/3 mr squared, 2/5 mr squared. That's for us old people to memorize. All right?
Yeah.
Okay. All right, so we've identified that we can put this into our equation. So let's do that. I'm going to do that on this side. T equals 1/2 mr times A over R. One of the things you should notice is that often the R's will cancel out. Do you see that they cancel out here? So T equals 1/2 MA. Now, you have two things that you can bring together. So it's a lot of the same steps, just repeated for torque. And having to do this is something that you're going to have to get accustomed to thinking about. Now I can just substitute mg minus 1/2 MA equals MA. You can finish this, right? You can solve this for A. You should be able to. Do so, please. All right, Carson, what'd you get? What's that? Let's do so. Sure. There's an M in every term, so I can get rid of all the M's. What should I do next? I believe in you, Carson. Don't leave me hanging. I want A by itself. Yeah. Sure, I could add 1/2 A to both sides. Sure. Way to go. Good job. That's the words, the parallel axis theorem. You'll have to use the parallel axis theorem to do the problem. Try.
At the beginning.
Pointing at everything.
No, I'm starting at the beginning. Net torque equals I alpha. Good.
Plug in, okay, where the, oh wait, what did you say?
I'm starting at net torque equals I alpha. You said to start at the beginning. I'm starting at the beginning, right here at the top. Let's.
Is that using the parallel axis?
Well, eventually, I'll have to get there. So I'll right here. Which side do you want to work on first? The left side or the right side?
The right side.
The right side. Okay, so you're right. We'll have to do the parallel axis theorem.
Okay.
What is the parallel axis theorem?
The ICM plus MX squared.
ICM plus mx squared. Excellent. So ICM is the moment of inertia about the center of mass. So that's 1/2 mr squared. That's what I gave you.
I thought CM meant centimeters. Now it's
Well, then you should probably write more things down in your notes.
yeah.
Okay. CM stands for center of mass. The parallel axis theorem shifts the axis of rotation from the center of mass to another parallel location. How far am I shifting the axis of rotation? I'm shifting it 1 radius because I'm going from the center here to here. That is 1 radius. Okay, back over here because you wanted to work on the right side. We're working on the right side still. Plus mr squared. I shifted it 1 radius. This still not hard, I don't think yet. But if you thought cm stood for centimeters, you were screwed. You're right. Let's keep going now. What's 1/2 mr squared plus mr squared? What was that?
Well, that's just like a fly.
Oh gosh.
Oh, I wish. It's a mosquito.
Good riddance from the world.
I don't like mosquitoes. Do you like mosquitoes? Okay.
Just unexpected. That's
I think I did the world a fit. Well, if you don't act fast, it'll just fly away, right? Aren't you happier that we rid the world of one more mosquito?
you took a frog away from breakfast.
All right. Carson, what's 1/2 mr squared plus mr squared? Thank you. Just making sure that we're still able to do the algebra because I was a little concerned about a minute ago. All right, so looks like you got the right side handled. Kind of. Right, we got the I portion handled. Not done yet though. What are we gonna do on the left side? Who should I pick on for this one? I'd say Carson again, but I really don't want to keep going to that well. So let's try somebody else. All right, Xavier, what do you got?
What the heck?
Feel that bus? How'd it feel?
I don't know, I get it.
I need net torque. So what is causing a torque about the pivot point?
Well, nothing. Just the 2 points.
Well, if the pivot point is here, are there any forces that are acting with a torque arm distance greater than 0?
MG.
mg. All right. So I looks like I do have a torque acting. mg is pulling with a torque arm distance of r. I just got to turn that arrow around and draw it this way, right? So the torque arm distance is r, and the size of the force is mg. And is that 90 degrees still? Looks it. Sine 90. All right. Looks good to me. So I guess the only final question is that true? Was it true before? It's true now. So R mg equals 3/2 mr squared times a over r. Can you work that out for me, Carson? Good, good. I'm worried about your algebra. But I might call on somebody else. I've got other people to pick on, like I could call on Nathaniel. I always think he's listening to music. He's always got the right AirPod in. Unless I'm on that side of the room. And then he has the left AirPod in. He switches, depending on which side of the room I'm standing on. So like I don't see it, but I know it's there. He writes Nathaniel on all of his paperwork. So Nathaniel, what do I get? What if I was solving this for A, what would I get? Oh.
He was too busy taking off his AirPods.
You get the same thing. You get 2/3 G over A. Or is it equals A?
I do. I get 2/3 G, just like before. Right, all the R's cancel, and the M's cancel. I get the same answer. In fact, I'd say that if I had done it that way from the beginning, it would have been easier, right? It was less work, but I had to use the parallel axis theorem. So, your notes. If you're trying to figure some stuff out here, it appears that choosing a pivot point doesn't really make a difference as long as it's a reasonable pivot point. I think the center makes more physical sense in my head, but this is clearly a pivot point too. The truth is, it actually does pivot about this point. That's the way things roll. They pivot about that point. They don't pivot about their center. But it doesn't really matter which of those you choose. You get the right answer either way. There's nothing wrong with this problem. You see that now, I hope. And you were asking, what if I wanted to make this one where A and alpha were less connected? Anybody ever use a yo-yo before? Is anybody an actual yo-yoer? Like you can do the thing with the yo-yo? You're a professional?
No.
Okay, because I'm thinking you'd have to prove it. Who can do the thing? Do you know what I'm talking about when I say the thing? When you drop it and it stays down there for a second and then by magic you make it come back?
I knew how to do it.
What's it called?
I need to witness.
It's not called a trick. It has a name.
I need to witness this yo-yo trick. I've never.
I'm so disappointed in all of you. It's called walking the dog. So, Nyla, look, I've taken it easy on you guys today, but Nyla, if this were a yo-yo, do you see how the size of the disc would have one radius, but the part that's unrolling would have a different radius? This might be a circumstance where the 1/2 mr squared for the disk would have one r, but the A equals alpha times r would have a different r. Do you see now why you have to ask yourself if the r's are the same, if they're connected together? It just has an R in the answer. It's not as complicated as it looks. But this is the kind of thing where you'd end up having the little r in your answer somewhere and probably the big R in your answer somewhere too, because they wouldn't cancel out.